Hello, Professor. My name is Abhishek Dandu, and today I'll be giving a brief presentation on the article X, a protected data plane operating system for high throughput and low latency. Going forward, uh, I'll be giving a brief introduction on the abstract. First, a data plane operating system is used for high performance networking where it exceeds current kernels in I/O speed while maintaining the robust security they are known for, and it decreases the tail latency and boosts the throughput, which makes it a popular key value storage considerably quicker and more dependable. Ultimately, it offers a convincing answer for high performance networking in a secure operating system environment. Coming to the next slide, a data plane operating system that utilizes several new architectural choices uh, meets its high I/O speed and low latency goals. The hardware visualization it offers has strong security without a detrimental effect on throughput by separating the control plane from the network operations. Throughput and tail latency performance increases when a well-known key value store is moved to data plane operating system. The experimental evaluations reveal that X outperforms Linux and the most cutting edge user level network stacks regarding the throughput and end to end latency. There are a few key definitions that we have to uh, go through, which were discussed by the author. They are they recommended the data plane operating system, which separates networking data processing from control plane operations to enhance networking data processing. It utilizes VMX non-root mode hardware visualization that separates the control plane and data plane. The control plane is the area of the OS that is maintained apart from access data plane and is in charge of resource management and system call execution. Data plane instances are autonomous, segregated components in charge of in kernel network processing. According to the authors, the data plane operating system separates the networking and data processing paths, enabling it to reduce kernel overhead and provide an event driven cooperative multitasking architecture to enhance performance. Isolating the data plane from the control plane using VMX non root mode in X's hardware visualization strategy ensures security and gives network processing a specialized environment. It provides high performance data transfer which has made possible via the zero copy API, which enables effective data interchange between the network stack and applications. The purpose of the study or the goal of the study was to present that a novel data plane operating system and highlight its performance benefits over more traditional approaches. Using hardware visualization, the author separated the network bound applications, the data plane instances, and the control plane into into their own distinct parts. In a variety of networking micro benchmarks and the widely used event-based applications, memcached, the experimental research showed that X beat Linux and MTCP. The findings demonstrated that X is a fantastic option for data center applications since it can quickly saturate four times the 10 GBE system with a lot of concurrent connections. Research design. A group of network applications and workloads in data center environments constituted the population studied for the research project. The servers and clients both had Intel X520 10 GBE NICS installed. A unique benchmark was used to analyze throughput and scalability while NET pipe examined latency. The authors additionally examined X as a practical event based application using Memcached, a popular in memory key value store. Using the multi-late load generator program to simulate various workloads typical of real world usage scenarios, they assessed throughput and latency. Finally, they used the multi-late load generator tool to assess the performance advantages of X with Memcached, a frequently used key value store. For two separate workloads that were reflective of actual usage scenarios, they assessed throughput and latency. The results showed that utilizing X in comparison to Linux significantly increased throughput and decreased tail latency. There were a few findings from this uh, research, and this study revealed a number of significant findings and results. The testing demonstrated that X performed better than Linux and MTCP regarding latency and single flow bandwidth. The data plane operating system only needed 3 cores, but when compared to MTCP, which needed all 8 cores to overload the 10 GBE connection fully. The data plane operating system grew more quickly and aggressively compared to MTCP and Linux regarding performance and scalability, as it sent 8.8 million messages per second, which is 8.8 times faster than Linux and 1.9 times faster than MTCP respectively. These trials also showed that data plane operating systems scaled quite effectively up to a 4x 10 GBE configuration from 10 GBE. It also further demonstrated exceptional connection scalability, dispatching Linux while managing a high volume of concurrent connections by a factor of 10. These results demonstrate that the data plane operating system improved performance, scalability, effectiveness compared to other conventional methods. Overall, the results showed that the data plane operating system is better than the traditional ones in terms of performance scalability and latency reduction. Uh, there are few strengths and limitations as well. And while doing this research, the analysis that was performed showed a comprehensive and competent effort of reviewing pertinent, pertinent works and literature. Discussions and comparisons with the author's current work on topics like Arrakis, exokernels, asynchronous and zero copy communication systems, and library operating systems were made. They performed a great job of highlighting how their work was unique from and improved upon earlier approaches. The researchers employed respectable and trustworthy techniques such as NET for throughput measurements and latency analysis to further support the accuracy and rigor of their findings. By offering a thorough analysis of the advantages and disadvantages of X data plane operating system, this essay made a significant contribution to this disciplines of network and OS. Future research implications show that, according to the article's finding, network applications in data centers can benefit from the high performance and low latency that the data plane operating system can provide. The findings demonstrate that by separating the control plane and the data plane, utilizing hardware visualization, and using adaptive batching, throughput may be greatly increased and tail latency reduced. Also mentioned are uh, excess benefits for handling several simultaneous connections. It would be interesting to conduct more study on access suitability for non-volatile memory access and interoperability with other network protocols. More research in these areas may provide insights on access potential uses and implications for data center connections in future. Background and motivation. The article centered on enhancing operating systems for multi-core servers running applications with demanding network needs. Large-scale data center applications provide particular difficulties for their networking stacks and system software. The requests and frequently the responses between the numerous services that make up a data center application are relatively modest regarding high packet rates. For instance, with Facebook's memcached service, most queries have values and critical lengths of under 500 bytes, and each node can scale or handle millions of requests per second. Applications must be isolated from one another for protection. There is a requirement for application isolation since various services frequently share servers in both public and private data centers. Last but not the least, daily patterns and spikes in user traffic for resource efficiency cause a considerable variation in the load of data center applications. The hardware OS mismatch. In this, we'll see that the modern servers should have sufficient of hardware resources to support high packet rates and low latency for data center workloads. Tens of hardware threads working along with 10 GBE NICS should enable speeds of at least 15 M packets per second with the smallest possible packet sizes. Unfortunately, many different hardware assumptions were used while designing commodity operating systems. The notion that numerous programs would share a single processor core and that packet interarrival delays would be significantly longer than the latency of interrupts and system calls informed the design of kernel schedulers, networking APIs, and network stacks. These operating systems compromise of speed and latency to prioritize fine-grained resource allocation. Throughput is constrained by the increased CPU and memory system overheads caused by the buffering and synchronization overheads required to provide flexible, fine-grained scheduling of workloads to cores. Going to the next slide, there are quite a few alternative approaches. Numerous other strategies have been proposed since the network stacks included into commodity kernels, which are unable to take use of abundance of hardware resources. These include user space, networking stacks, alternative to TCP, alternatives to POSIX API, and OS enhancements. Uh, this slide states the approach towards the design of the data plane operating system. Microsecond latency and high packet rates, the first pair of requirements in 2.1, are not specific to data center applications. Before moving on to the next packet, a packet's network protocol and application processing are completed. It improves the data plane architecture to support all 2.1 requirements and handle general purpose untrusted applications. The data plane, which manages the networking stack and application logic and the control functionality of the kernel, which is in charge of resource management, provisioning, scheduling, and monitoring are separated by operating system. Coming to the implementation, each of the steps required to receive and transmit a packet are completed by X data planes, which interleave protocol processing in kernel mode and application logic at clearly marked transition points. The Linux kernel initializes PCIe hardware, including NICS, and offers the fundamental methods for allocating resources to the data planes, such as cores, memory, and queues. Data plane API and its operation. The data plane, which is comparable to a library OS but with memory separation, is distinct from a standard kernel in that it is optimized for high performance network IO and only executes a single application. Our data planes still offers a lot of well-known kernel level functions, though through stacked paging, the data plane additionally oversees its own virtual address translations. In contrast to modern operating systems, it only utilizes huge pages. Those are almost equal to 2 MB. Multi-core scalability. This is a more stringent condition than lock-free synchronization, which calls for pricey atomic instructions even when only one thread utilizes a certain data structure. First, only commutative APIs can provide synchronization free system call implementations. The commutative between elastic threads in the Access API. An elastic thread cannot directly conduct operations on flows that it does not own since each one has its flow identifier namespace. The API implementation is also meticulously optimized. The memory pools, hardware queues, event condition arrays, and batch system call arrays are all managed by a separate elastic thread. And each elastic thread runs on a distinct subset of TCP flows thanks to the NICS implementation of flow consistent hashing. Security model. A cooperative flow control mechanism exists between the application code and the network processing stack in the Access API and implementation. The access protection architecture makes few assumptions about the program in contrast to user level stacks, where the application can be relied on for proper networking behavior. Applications that behave incorrectly or maliciously only do harm to itself. It won't damage the networking stack or have an impact on other programs. IOMMU utilization is not yet encompassed in the current X prototype. Evaluation. In the experimental arrangement, a Quanta or Cumulus 48x 10 GBE switch with a Broadcom Trident ASIC linked a group of 24 clients and one server. At the time of writing, each machine had a conventional setup with an Ubuntu LTS 14.0.4 distribution running the most recent 3.1 16.1 Linux kernel. The experiment initially assessed access latency using 10 GB setup and the well-known ping pong test and NET pipe. The research also looked at access throughput and multi-core scalability using the same test as Megapipe and MTCP. Each client performed the synchronous remote procedure call n times before disconnecting. The connection scalability of access configuration, uh, the 4x 10 GB configurations, excess scalability for managing several concurrent connections was also evaluated. There are n threads operating on 18 client computers, each of which continually calls the server with 64 bytes remote procedure calls using a configurable number of open connections. As per the expectations, throughput increases, a connection concurrency grows, but it falls off for very high connection counts due to the rising cost of multiplexing among open connections. Memcached performance. The advantages of data plane operating system for performance. Memcached, a popular in-memory key value store developed on top of the live event framework, was the final component to be evaluated. Memcached is a network dependent program with threads executing in kernel mode for more than 75% of its execution time. In the end, the IOMMUs of VTD are not yet utilized by the present X implementation. Instead, it uses the Linux page map interface to identify physical locations and maps descriptor rings straight into X memory. Finally, I conclude that this article talks about the data plane operating system, which separates and isolates the Linux control plane, the instances of data plane that do in kernel network processing, and the network bound applications executing on the top of them via hardware visualization. The data plane design eliminates synchronization on multi-core servers and processes limited groups of packets until they are completely processed, thus optimizing for the bandwidth and latency. Thank you, Professor.